Welcome to the course on advanced power electronics. So we'll cover today's topic on switch electronics motor types. Coming to with the outline of presentation, so we'll discuss like a working principle and types of switch electronics motor, dynamic modeling of switch electronics motor, and control of switch electronics motor type, and case studies on switch electronics motor type, inclusive power quality improvement in switch electronics motor type, and design and control of solar PVR files, switch electronics motor type for water pumping system, and for example numericals and references. These typically the concept of switch electronics motor. As you can see here, we excite the ideally one winding at a time, and the rotor is a simple electromagnet to which get attracted by the excited pole, and that gives the polarity motion. And on the right side, you can see the animation how it is inside, and then you can see typically physically photographs also here on the right side on the bottom, that how really the motor looks like. So you have a concentrated winding on the rotor, only of 3 poles, and you have a cylinder on both starter and rotor, and you can see the cylinder rotor, and you can see a flooded form of this also. So the origin of this motor can be traced back to 1842, but the reinvention has been possible due to advent of inexpensive high power switching devices. So since 1969, a variable reference motor has been proposed for variable speed applications. So reluctance motors are doubly silent, singly actuated electric motors with passive windingless rotor, and their concentrated coil phases are turned on sequentially to produce torque through DC voltage pulses, which result in unipolar control current. So the power rating of reluctance motor ranges from 3 watt to the practically megawatt units, and it can work for low speed control range, low dynamics, as well as the high grade servo application, especially in thermally and chemically harsh environment. So the type of machine is differentiated by the number of poles on stator and rotor. So configuration are available 6 by 4 means 6 pole on stator, 4 pole on rotor, similarly 8 by 6, 10 by 8, 12 by 8, and 12 by 10, and many more other configurations. So these is the applications. I mean, like starting from aerospace, we have a solar water pumping, then mining, then marine propulsion, door actuator, collector, medical application, home appliances. So these are the, and you can say basic principle how really the through this animation, how the motor moves the excitation for some duration. Normally one phase, but for commutation period, sometimes 2 phases are also excited. That's on it. So there is typically a kind of medium power application adjustable speed drive you look into, and we have a application in textile industry, as you can see here, because of variable speed requirement. Then oil field pumps, electric screw press, then mining machinery, then precision position control servo drive, and vacuum cleaners, then aircraft applications, then conveyors. Then the major application in home appliances for low power application is like a food mixer, then vacuum cleaner, fans, then typically the like many kind of tools, air conditioner, refrigerator, and typically the washing machine. Then coming to follow up of what the basic concept is here, we have a power factor correction converter with a midpoint converter for 6 by 8 by 6 modes, as you can see here, and then all these are used normally for ceiling fan, washing machine, air conditioner, food blender, and refrigerator. So another major application of medium power is the application of solar photovoltaic array fed water pumping system. So solar water pump for irrigation in sprinkler, and the another application is aerator machine with aqua farming and solar pumping swimming pool. Then the solar water fountain, domestic and municipality supply, and solar pump water heating system, and lively stock system. Then the RO system, civil industrial and mining, and the electric vehicle, and typically for a different kind of phase with the starting low speed turning, acceleration, high speed turning, and then the acceleration or regenerative brake. So here we have a 4 medium power like a electron motor drive system, as you can see here, and we have a typically the control of the speed. So we have a given speed, then we have a rotor is typically speed regulator, then here's the power converter, and then we have feedback from for the commutation as well as for protection purpose. You can see how it is placed in the your typically a 4-wheeler car with the battery to DC converter, then we have typical converter for SLM type as well as typically from fuel cell आता है. And this is typically land in application of electric wheeler, especially Land Rover Defender. So in electric research vehicle, the standard diesel engine and gearbox of the Land Rover V5 and SR drive and 740 kilowatt 94 bhp Swiss motor, electric motor. So the typically for this Land Rover, it was tuned with the 300 volt lithium-ion battery with a capacity of 27 kilowatt hour, giving a range of more than 50 miles, and it had top speed of 70 miles per hour. And in typical low speed off-road use can run up to the 8 hours before recharging. So reluctance motor technology developed by Nidec is exceptionally well suited to the Defender Audi's all-terrain traction needs, being able to deliver full rated power over a wide speed range. So this typically for but because of reluctance motor deliver 330 Newton meter of torque from standstill still, there is no need for gear shifting, and transmission comprise single speed 2.71 reduction gearbox combined with the existing Defender 4-wheel drive, as you can see in the photograph. And these are some more photographs with the 2 kilowatt 4 quadrant high performance pallet truck drive and battery powered electric vehicle with the SRM drive. So now another is a hybrid bus. So in green population, series and parallel hybrid transmission scheme, a 50 kilowatt and 160 kilowatt SR drive motor generator both work in conjunction with a 2.5 liter diesel engine, downsized from 7.5 liter in a conventional bus. And this combination is powered from lightweight, low loss lithium polymer batteries and enables the vehicle to seamlessly switch between the pure electric running or hybrid power, whichever offers optimum efficiency. So the technology also eliminates the need for a main gearbox, enabling direct coupling to the wheel drive, resulting in improved efficiency at all operating speeds, as you can see in the photograph. So in test, green population combined hybrid system achieved reduction in CO2 emission in excess of 40% and fuel saving of over 30% compared to the conventional diesel engine vehicle. And other key features of the green propulsion scheme is the use of low loss lithium polymer battery that provide significant weight saving and improved electric efficiency compared with lead acid battery. This is typically the different parts of this hybrid bus drive, where the 50 kilowatt motor and your 130 kilowatt peak are used. So the result is a design which meets all the performance requirement and has been demonstrated to be most cost effective solution when compared with other electric drive technology, costing some 25% less than alternative systems. And the 15 kilowatt SR drive motor generator provides a up to 120 Newton meter assist during launch and yields an anticipated 10% improvement in the fuel economy. And this is a hybrid power. Typically, the 10 key parameters of the SRM drive motor generator are given here. All the dimensions like your stator laminations 284, typically, and as well as your stator active length 55 mm, and rotor laminations 197 mm, air gap 0.4 mm radius. Then minimum battery voltage performance 107, low speed peak torque 120 for 60 seconds, low speed continuous torque 70 Newton meter, and base speed 15 kW at 1200, and maximum design speed is 6000 rpm. So another industry is in India, like Eddy Current Drive Limited, which is manufacturing this, a public limited company established in 1971. Eddy Current introduced India first Indians to develop electric car. The company manufactured electric car using reluctance motor for each propulsion. The company has manufactured facility at Chalkudi, Kerala, and Kubatur, Tamil Nadu, as you can see in photograph. Coming to now reluctance motor construction and details and operation. The reluctance motor are operated with only one active phase at a time and can be operated with 3 or more phases. The number of rotor and stator poles must be different. The number of rotor poles and may be less or more than number of stator poles, but less number of rotor poles are preferred. And reluctance motors are made of laminated stator and rotor core with NS equal to 2 MQ poles on the stator and NR poles on the rotor. The number of phases is M, and each phase is of concentrated coils placed on 2 stator poles. And this is typically how 2 phase 4 pole 2 is typically pole switcher, but for such a case, you require a very special kind of rotor construction with some increased gear upon the person on one side of it. The typically 3-phase 6-pole, 4-pole stator, 3-phase 4-pole stator poles motor. This is your 4-phase 8x6 and typically single-phase excitation system, as you can see here. Then this is the cross section of 6x4 SRM, and then the cross section of 2 phase of, and then these are cross section of 4-phase 8x6 motor, as you can see here. So, and this is 5-phase your 10x8 motor. So coming to now primary features of reluctance motor. Reluctance motors is a brushless AC motor. Primary winding is on stator only. The rotor contains no winding conductor or permanent, and use electronics commutation rather than mechanical brushes, commutator or silvering. Rather simple low cost machine. No operation over a wide temperature range without performance degradation due to the absence of magnet, and highly efficient motor and inverter, and high speed power output per weight and volume. So the second features of this reluctance motors are very high speed capability, high starting torque capability, unipolar phase energization requiring a minimum of 1 switch per phase, and very high torque to inertia ratio for good acceleration and reversing characteristic, and useful open circuit and short circuit characteristic. Very long life and reliable machine with inverter life comparable to the other inverters, and operating characteristic can be easily programmed, and converter is illuminated to so throughput. So cannot operate from AC line power without some sort of converter or controller, and very high audible noise proportional to speed, relatively high torque ripple, and speed versus torque characteristic is highly nonlinear, and requires very small mechanical air gap to achieve high torque versus volume or weight, and requires soft position feedback data for phase commutation, most complex wiring connection compared to other. And this is typically in order to establish a reluctance torque, a stator phase is excited as unaligned position displayed by A in the figure, and by magnetizing the stator pole, the closest rotor pole will be magnetically polarized and will experience an attractive force. So the tangential component of this force substantiates an electromagnetic torque in the direction which reduces the air gap length, and the shape of current is usually controlled such that a maximum torque per ampere is generated. And as the rotor approaches the aligned position shown by in the figure, the radial component of the attraction force becomes dominant and the tangential component reduces to 0. Therefore, it makes economic sense to remove the current before the aligned position. And the shaded area in the figure depict the magnetic energy converted into the mechanical form, where the area denoted by R demonstrates the magnetic energy that has not been converted into useful work. And this is typically alignment of the poles of stator in different positions. And this is typically in case of 4-phase 8x6 motor, how the inductance variation is there with the rotor position. So we have a 4-zone rising inductance, falling inductance, then maximum inductance, minimum inductance, and these all poles are depends on the design, whether you are designing for low speed or high speed machine. In low speed machine, usually these zones are, especially flat, low inductance and high inductance zones are quite small, but high speed these you have to increase because you want to commutate the current well before it goes to your rising or falling inductance from operation, like in other side. And these are typical case how really we save on high speed. When we excite little before the full voltage, then only the current get established, and then but we also commutate when little before even then your rising inductance profile, because current will take time to take the quiz, and you can clearly see from the waveform, how really the voltage waveform across the winding is there. This is for a case is for high speed, then further high speed, and then further high speed. In first case, you have a certain current commutation, flat portion, but as you go further for the high speed, then current difficult to even to push the current with full applied voltage. And this is typically again the inductance. So ideally we should excite in rising inductance zone in the middle, that really gives the maximum torque, but of course you will get a lot of commutation ripple. So you have to really excite for a little longer period along with another phase also. So coming to now linear analysis of the
volt current equation and torque production. So the inductance is unaffected by the current, that is, there is no magnetic saturation, and mutual coupling between phases is normally 0 or very small and is no good. And the voltage equation of one phase is V equal to Ri plus d phi upon dt equal to Ri plus d Li upon dt, or equal to Ri L di by dt plus I dl upon dt, or equal to Ri plus L di upon dt plus I dl upon dt and d upon dt, that is equal to Ri plus L di by dt plus omega m I into dl upon d theta. So where the V is the terminal voltage, I is the current, phi is the flux linkage in the volt second, R is the phase resistance, L is the inductance, phase inductance, theta is the rotor position, and omega m is the angular velocity in radian per second, and the last term is sometimes interpreted as vacuum equal to omega m I dl upon d theta. And the instantaneous electrical power is Vi equal to Ri square plus Li di upon dt plus I omega m I square dl upon d theta. Rate change of magnetic stored energy at an instant is given d upon d theta in bracket half Li square, that becomes half I square dl upon d theta plus Li d upon d theta, or equal to half I square omega m dl upon theta plus Li di upon d theta. So mechanical power conversion is P equal to T into omega E, or mechanical power can be written as P equal to P in minus Ri square minus d upon dt half Li square, and then from this equation torque is your half I square dl upon d theta. And this is a three-phase SRM with major dimensions variable. So why we have a less rotor poles than the stator generally? Sometimes maybe even different also, but there are reasons. So SRM may have more rotor poles than the stator, as it leads to a smaller stroke angle and low torque ripple, and lower. However, it suffers from following drawback: lower inductance ratio, higher core losses, increased speed rating of the controller, decrease in the specific output. Therefore, SRM are preferred with large number of stator poles, with advantages like high inductance ratio, reduced copper loss, shorter frame size, decrease in underlying inductance. So SRM should have more than 2 phases for successful operation, because the value of absolute overlap ratio is required to be at least 1 to make the motor capable of producing torque at all the rotor positions. So the absolute overlap ratio is the ratio of absolute torque zone, that is pi upon nr, to the stroke angle 2 pi upon stroke per revolution, that is 2 pi mnr, where n is the number of the rotor poles. So this ratio shall be m by 2, where m is the number of phases, and make it this ratio 1, and m has to be 2. So number of strokes can be increased with the more phases without increasing the number of rotor poles, and the torque dips are removed with the more number of phase excitation. And this is, you can say, why higher number of phases number comparison for the torque ripple. So we have 3 phase, you have a very small overlap and you have a large torque ripple, and if you have a 3 phase, you have a small torque ripple, because you can go for overlapping also. But in 5 phase, you have further less ripple, because you can even have a reasonably overlap like next that. So look into this align and this align position, showing the two different, only 2 pole for illustration, and this is the your flux distribution in SRM. So now coming to property of your rotor position, under align position is at theta equal to 0 and 180 degree. This position gives maximum inductance. Maximum magnetic circuit is liable to saturate, zero torque because of stable equilibrium. And typically an aligned condition, aligned position is at theta equal to plus minus 90 degree. This position gives the minimum inductance and magnetic circuit unlikely to saturate, and zero torque, unstable equilibrium. So coming to now selection of poles, phases and winding. So if the poles are wound oppositely in pair to form the phases, then each phase produces a pulse of torque on each passing rotor poles. So the fundamental switching frequency in one phase is therefore F1 equal to n, small n, capital Nr, where n is the speed in radian per second, RPS, and Nr is the number of rotor poles. So if ringing is neglected, there must be an overlap between a pair of the rotor poles and the poles of the excited resistor phases, and in this case torque can be produced through an angle beta, which is the smaller of the stator and rotor pole arc. To produce a uniform torque, beta should be greater than eta, where eta is the stroke angle. So in order to get turn rotor pole arc, in order to get the largest possible variation of cage inductance in the rotor position, the inner polar arc of the rotor must exceed the exterior pole arc, that is 2 pi upon nr minus beta r should be greater than your beta s, and this ensures that when the rotor is in the unaligned position, the relative to the exterior poles of one page, and there will be a no overlap and therefore a very low inductance. A further constraint on the pole arc is that usually the exterior pole arc is made slightly smaller than the rotor pole arc, and the constraint on pole arc can be expressed graphically shown in next line, in which the feasible triangle defines the range of the combination normally possible. And these are typically for 3-phase 4-pole. So you can design the motor within the triangle only in both the 3-phase as well as 4-phase motor. So now coming to the linear analysis of reluctance motor. The linear analysis assumes that the inductance is unaffected by the current, there is no magnetic saturation. So for simplicity, the pinging flux is also ignored. The instantaneous torque is T equal to d omega c dwc upon d theta at the I constant, or equivalently T equal to minus d wf divided by d theta at the I constant, at typically I constant. So field energy wf is minus I d lambda, and co-energy is wc equal to integral lambda di. So now the flux linkage is lambda equal to li, and the field energy stored and co-energy become equal. In this case, w equal to wc equal to half li square, and therefore the developed torque half I square dl upon d theta, where dl upon d theta is the slope of inductance variation. And in case of now coming to nonlinear analysis of SRMA, you can see the characteristic flux linkage and current characteristic is nonlinear here. So in a nonlinear analysis, the stored magnetic energy and co-energy variation is assumed nonlinear, and the value of flux linkage is calculated lambda equal to as the integral v minus ri into dt, and from the voltage equation v equal to ri plus d lambda upon dt. So assuming that the flux linkage is function of current and rotor position, that is lambda equal to lambda function of I theta. So now coming to following expression are u. So d lambda upon dt equal to v minus ri, and d omega upon dt is t minus tl, and d theta upon dt is omega, and the stored energy wf is defined as wf equal to I integral I d lambda, and where lambda is a function of I theta. And this is, you can see how the linear, non-linear, but you can see in non-linear case you have a large area which is responsible to do the work. So this area represents to do work, or you can call it the energy in case of Stokes angle. So the typically ideal inductance of the symmetry of magnetic circuit leads to the almost zero mutual flux linkage in the SRM phases even under saturated condition, and this means that the SRM may work with m-1 phases since there is no induced voltage or current will appear in the short circuit phase. Like, and these are typically the, you can call it the ideal and motoring, as well as the typically generating rising inductance, which will certainly excite the then it goes motoring torque and motoring current and generating current, and accordingly when you go for high speed, you can see how the current excitation is there advancing and how the current takes place here and how in the region. And this is typically how the your typically phase inductance profile with respect to the current profile. So you put excitation little before, and but you can little before also for till get aligned. So coming to overlap angle, as the rotor rotates, the inductance varies between the two extreme values, and the overlap angle between the stator and rotor poles is alpha, and alpha equal to theta minus theta x, and where that theta equal to between theta x theta y, where theta x equal to pi upon r minus beta r plus beta s by 2, and theta y equal to pi n upon 2 pi upon nr minus in bracket beta r minus beta s divided by 2. So to produce the torque of all the rotor position, the entire 360 degree must be covered by segments of rising inductance from different phases shown in the next slide. The phase current must be commuted and sequentially to coincide with the appropriate segments, and a small amount of overlap is desirable to minimize torque ripple in the form of notches at the commutation instant. This is typically the commutation scheme. You can see typically 3-phase how the current, ideal currents will be there, how the practical current waveform at low speed, and how the practical waveform of current at the high speed, you can see. And this is typically how the commutation strategy. So we excite with the full voltage, then we go to control voltage to limit the current or to maintain, and then we quench it. So you can clearly see practical how the voltage is there applied across, and how the current your stationary established, maintain, and then quench. Compared to this already we cover it. Now coming to the average torque, the torque is produced in impulses as the rotor rotates, and the instantaneous torque in terms of the rate change of the your co-energy at constant current. The average torque could be calculated by integrating T over the one cycle, that is one rotor pole pitch equal to 2 pi upon Nr, where Nr is the number of rotor poles, and dividing by tau. So in one cycle of operation, the maximum possible energy conversion at a current I in the area W enclosed between the underlying magnetization curve U, the underlying magnetization curve A, and the vertical line UA at the current I. So if the S is the number of stroke per revolution, the electromagnetic torque is NS. Nm is equal to T average SW upon 2 pi. As you can see in the area, what is the SW? Typically stroke energy, number of stroke multiplied this stored energy W. And this is the torque speed characteristic. So at low speed we operate in constant torque, and high speed we operate constant power mode, where torque is inversely proportional to speed. And then we have a very normal, this series very high speed, that is torque proportional to 1 upon omega square. And this is typically torque variation, and you have a typically because of saturation you have a variation, as well as during the commutation also you have variation. So ripple are there in the torque. Of course, waveform 3-phase reluctance motor, the different. If you apply pulses of the voltage, then the hysteretic flux you can say look like triangular, then hysteretic core flux which overlap, and then the hysteretic core flux 2, as you can see in the part, as well as rotor core flux, and then you have a rotor core flux like. And these are the typically normalized flux linkage versus current, and your inductance versus theta, and then you have a torque versus your theta at different currents, and similarly here torque versus speed. And your low speed and high speed operation, and this cross sectional is a 4-phase 8x6 motor, and this is the phase connection of 8x6. So you have a 2 switches for each phase. In classical, so a phase you are exciting, so when we close the switch, the voltage is applied, and then you can open either both through diode. There is a path negative voltage is applied, or you can switch off only one, so freewheeling action take place during, and finally you have to switch off both. Like, and these are the inductance variation for all 4 phases which have a phase shift, and these are the typically rotor pole pitch, and how the you excite by the DC current, how the torque produce positive torque and negative torque due to the, and this is the current. I mean, typically at low speed with the inductance, and typically high speed how the current is there. And this is typically the torque profile with the you can call it the different kind of motors. And on the left side and right side you have a universal motor. How better than universal motor this take place on the higher side, and of course there are many manufacturers replace the universal motor by reluctance motor. Because then in noise, it has a much lower noise at 800 rpm compared to the induction motor, as you can see. And these are the torque profile for typically the with the torque speed, and then of course as reluctance motor I then class F insulation. So and then the efficiency contours and torque versus speed. So here you will see there is a contour for maximum efficiency also. So you can get a maximum efficiency over a wide load range. And this is a typically power versus your efficiency. Then the torque speed. Then your typically the motoring and generating region of phase inductance change cycle. I mean rising your typically have a motoring, and falling your falling is the your for regeneration or for typically the reverse motoring also. So now coming to converter topology for reluctance motor. So we have a number of converters which are devised, but only P came challenging. And we can for Q-phase motor, so it may be 2-stage power converter, and 2 switch per phase, 2Q switch asymmetric with and variable variation of asymmetric with 2Q. Then the 1.5 time per phase, 1.5Q, then the Q+1 switch, equal sharing C dump with the field link, shared switch, minimum switch with the variable DC link like buck and resonant, then single switch per phase like R dump, pipe filter, split DC supply, then Q phase, Q switches plus 2 Q diode, then independent phase current control and dependent phase current. These are typically asymmetry of these, very popular, that you have a 2 switch for each phase. So we switch on both the IGBT, then current flows, and when you want to, you can switch off one device, like let's say upper, then you have a filling action through the diode, and as well. Similarly for upper also you can do that for all the phases. This is another bifilar one. I mean, this winding with the opposite polarity is put on the same pole, and they are connected in this manner typically. So here also, when you really switch on the transistor, then the current flows, and typically when to quench, when you really open the switch, automatically the secondary side throw diode will recover the energy stored here. So this is typically the same waveform, but you can see how really the control is taking place using this. And this is split phase, which is also called, is for typically or even number of phases, and we are using the midpoint here also. So the advantage is it can be used even phase. So for phase only 4 switch are required in this converter, and this is the how the control is there. Commutation sequence. You excite typically both the transistor you switch on, so current flows through, and you switch on one, so one current flows, and when you switch off, then you have a field induction with another diode, and you can see the waveform also. This is your Miller circuit with your N+1, so 3 phase your 4 transistor are used, and upper transistor share among all the 3 phases. So ideally, we have to have only one device conductor, one lag conductor. This is another C dump kind of. So here also you can switch on the transistor, then current flows, then when you switch off the large inductance voltage, I mean some is stored in capacitor, but automatically some go through the diode automatically to the back, like. And these are basic operation, how really excite is there and what the kind of it. Then this is another operation, CDUM with the pre-zone. So here also we have a single transistor, I mean like, and then with the filling there, but this transistor sharing among the all. And this is the operation of this and waveform. Now coming to the your asymmetric bridge configuration for 4-phase SRAM as shown here in the figure. Coming to modeling of the SRAM type. So the modeling of reluctance motor drive consists of modeling of the speed controller, modeling of inverter, modeling of commutator, and modeling of the reluctance motor. So the derivative of the rotor position constant give the motor speed, and the motor speed is compared with the set reference speed and speed error process in the speed controller. The simplest controller used in PID controller, and many other can also be used, e.g. like sliding mode controller, fuzzy logic controller, etc. The speed error can sampling instant given by omega ek equal to omega star minus omega. So output of the PI controller at the kth instant will be take tk equal to tk minus 1 plus kp in bracket omega e or minus omega ek plus ki omega ek and plus kd in bracket e wek minus 2 wek minus 1 plus wek minus 2. So where kp, ki, kd are the proportional integral and derivative gains of the PI controller. So the complex control structure of the SRAM drive does not necessarily lead to the optimum stable performance by conventional pole placement technique. So the modeling depends on the type of inverter. In case of in this case 4-phase midpoint converter has been considered to energize phase 1. So if I1 equal greater than I1, then T1 is on, and I1 plus HV lesser than I1, then T1 off, and I1 minus HV, so greater than I1, then T1 is on. So de-energize phase 1, then T1 is off and D1 is off, and turn on angle means L minimum omega actual divided by VDC, and turn off angle is K I L max omega upon VDC. So the volt amplification starting will be VDC equal to L di upon dt plus L di upon d theta upon dt equal to Li d upon d theta, as omega equal to d theta upon dt. So theta equal to Li di upon Vdc. Therefore, turn on angle theta on equal to I L minimum W act divided by Vdc, and theta off is equal to K I L max omega act upon Vdc. So the winding excitation sequence is decided by the direction of rotation and inductance profile. So for forward motion, the sequence shall be 1, 2, 3, 4, 1 with the excitation in the rising inductance zone, and let the theta x1 equal to theta 1 plus theta 1 minus theta off, and theta x2 equal to theta 2 plus theta 1 minus theta off, and theta x3 equal to theta 3 plus theta 1 minus theta off. You are off, and theta x4 equal to theta 4 plus theta 1 minus theta off. So excitation of different phase winding is decided by the following logic. If theta is in between delta x1 to theta x2, then excite phase 1. If theta is between theta x2 to x3, then excite phase 2. Then theta is between theta x3 to theta x4, then excite 3. And then theta is between theta x4 and theta x1, then the energize phase 4. So now coming to flux linkage, expression as P lambda j equal to Vj minus Raj. Electromagnetic equation governing the motor behavior is P omega equal to T minus TL upon J, and P theta equal to omega, where T is the total electromagnetic torque developed, and give the T equal to summation of all per phase developed torque. So the torque developed by each phase of the motor is obtained by the inner co-energy as Tj equal to d omega dash upon d theta, where co-energy W dash is obtained from the linkage characteristic of HRM. So W dash equal to lambda di between limits 0 to I. Now coming to control scheme for reluctance motor drive. To control potentially an average torque is the result of the combined instance values of the torque from each phase, and the average torque is controlled by adjusting the winding current IP or the dual angle theta d. For the low torque ripple, it is advisable to keep the dual angle constant and vary the magnitude of winding current, and in one cycle of operation the maximum possible energy conversion at a current I is the area W enclosed between the underlying magnetization characteristic U and the underlying magnetization characteristic A, and the vertical line UA at the current I. And this is typically how the current is there and torque produced is there under ideal condition with the inductance variation. So coming to now control, so we have a position sense, then from which we really calculate the speed, and comparing reference speed, it gives the speed control. Typically, the output of the speed controller is typically as a sine as well as the magnitude of the current goes to the reference current generator, which is called commutator also, and we have another input like turn on turn off angle calculation, and we get a 4 reference current I1 star, I2 star, I3 star, I4 star. Then by through sense current, we really put 4 stage current controller to give the signal to IGBT based midpoint converter. So, and this is how really typically your ideal excitation system is on there practically. And these are the of course waveform at different speed current. I mean the typically 720 RPM, then you have a little advancing, then focus range reduces, and typically at higher speed of 1000 you can say 1 region how the waveform look, an experimental waveform for the sake of comparison. Now coming to current control technique, linearized current control design, then non-linear current controller design with the feedback linearization and decoupling without considering mutual inductance, and approach to considering the mutual inductance. So all of these approaches invariably use pulse width modulation to enforce current command, but the stage current controller known as a bang current controller is sometimes used in practice. So the outer loops are generally similar to those used in other types of motor drive, but the inner torque loop is specific to the reluctance machine. And the torque demand signal generated by the outer control loop is translated into the individual current reference signals for each phase. And unlike the DC or less DC motor, the reluctance motor drive cannot be characterized by simple torque characteristic KT and torque per ampere. Thus, in turn, imply that the drive controller must be specifically programmed for a particular motor and possibly also for the particular application. Now average torque control. At lower speeds, the torque is limited by only by the current which regulated. It is regulated either by voltage PWM or instantaneous current regulation. As the speed increases, the back EMF increases to a level at which there is insufficient voltage available to regulate the current, and the torque can then be controlled only by the timing of the current pulses. So this control is called single pulse mode or angle control mode, since the firing angle alone are controlled to produce the desired torque. And even at lower speed, with the voltage pendulum or current regulation, the firing angles are typically scheduled with the speed to optimize performance. Coming to converter advantage, a separate field link diode for each switch is necessary in all the SRM converter topology, which cannot be used to anti-parallel diode in the switches as in case of edge bridge inverter. So this may be mitigated by reducing the number of switches and also by the special converter module developed for the high volume applications, so that the overall converter cost can be reduced. And this is typically how the conduction and the signal. So you excite both the phases and how the current path is there. In different modes like, and which is given in the table. Now coming to typically soft switching, soft chopping. Soft chopping is only when one transistor is chopping, the other transistor remains on, and it is called the commutating transistor because its only function is to steer the or commute the current into the its associated phase winding at the beginning and at the end of conduction period. Coming to hard chopping. So hard chopping is when both transistors are switched on off together, and it generally produces more acoustic and electrical noise and increases the current ripple and DC link capacitor current for a given current ripple or the stress band, and it is necessary in certain conditions, particularly during regeneration, to prevent loss of control of the current waveform, and of course the final chop at theta c at the end of the conduction period in a hard chop. This is what the pendulum waveform with the soft chopping. You can see how the current goes and how the voltage chopping is there, flux increases, and typically the control architecture of single pulse control. So we have a with the typically the encoder and tacho, we get the speed, and we have velocity control, then we have position 4, so we get theta c and theta 0, and we give to pendulum controller which feeds to the motor and load. And this is with the typically with the, you can call it voltage control. So here we have a speed, feedback speed, and we have a typically the position also. So we get the duty cycle, and we have a shaft position. So with theta 0 and theta c and duty cycle, we give to pendulum controller which apply the voltage across the motor and load. And this is typically architecture current control. So we have a reference speed, we have a feedback speed, we have velocity control with the position also, we get the reference current, and then we get the commutation control also with theta 0, theta c with this current given to current reference, the current feedback to pendulum converter, and then that feeds through the motor. And this is typically the generator controller. So we have a DC link voltage reference, and we have feedback of DC link voltage, then delta VD give to voltage control, and we have a typically the speed and position feedback. So from this we get theta 0, theta c with due to pendulum converter, and which feeds to motor and load. Now coming to variation of current waveform with respect to the top speed. So low speed motoring. At low speed, the motor EMF is low compared to the available supply voltage Vs, and the current can be regulated by chopping, and the current waveform I is chopped at about 8 ampere starting 45 degree after the unaligned position and finishing 90 degree before the aligned position. At first, hardly any torque is produced because the inductance is low and unchanging, and when the approaching comes of the stator and rotor poles are within the phi degree of conjunction J, then the torque suddenly appears. When the driving transistors are switched off 90 degree before the aligned position, the current commutes into the diodes and falls to 0, so that the virtually no negative torque is produced. And this is the low speed operation 500 rpm, how it look like. Then you have you excite in each little before, and current is established and quench, and then you can see the torque profile. Torque is started only when the current start your rising inductance and then the flux. And you can see SI diagram how really portion of the complete SI diagram as a typically your stroke and energy source with the W. So coming to high speed motoring, at high speed the motor EMF is increased and the available voltage may be insufficient for chopping, and thus the torque can be controlled only by varying the firing angle of the single pulse of current. And in figure, the driving transistor are switched on at 50 degree and off at 80 degree. So just before the start of overlap, the inductance begins to increase and the back EMF suddenly appears with a value that quickly exceeds the supply voltage and forces dI by dt to become negative, making the current fall. And the higher the speed, the faster the current falls in this region. And this is a high speed motoring at 1300 rpm. You excite a little advance, then current is established and you go to single pulse mode. So after that we switch off, then torque produce, and then the flux rise and fall because of the applying. And then you can say portion of the your psi angle, how the psi I characteristic, how what much portion is get converted into the work. Coming to very high speed motoring at a certain base speed, the backcount rise a level at which the transistor must be kept on throughout the stroke in order to sustain the rated current. Any chopping will reduce the average applied voltage and this will reduce the current and torque. So peak flux linkage achieved during the stroke is given by Vs delta theta upon omega, where delta theta is the dwell angle or conduction angle of the transistor. And if the peak flux to be maintained at higher speed, the dwell must be increased linearly with the speed above the base speed. And typically at a high speed, the turn on angle can be advanced at least to the point where the sum of the flux linkage and defluxing interval is equal to the rotor pole width, at which the point conduction becomes continuous, that is current never falls to zero. Thus it appears that the dwell or fall flux building angle can increase from the 30 degree at very low speed to 45 degree at high speed. And this is how the current you apply full advance, and then how current builds up. You make sure that the J at least current are established, but current continues for longer period, and torque and flux, and how a small work is done because of high speed operation. So the energy conversion loop at low and high speed, so you can clearly see at 1300 rpm, 3900, the average torque is only about 1/3 of its low speed of value, but the power remains almost unchanged. So coming to low speed generating, the low speed generating is similar to the low speed motoring, except that the firing angles are retarded so that the current pulse coincide with the period of firing inductance, and the average torque is the negative, and the energy conversion loop is transverse in the clockwise direction. And this you can say low speed generating. You have a torque when falling inductance and torque is negative, and the flux linkage you can see the pattern and the stroke angle. So high speed generating, the torque is negative and the energy conversion loop is again transverse into clockwise direction. At the start of the stroke, there is a slight positive torque because the current is switched on a p degree before the lying position, while the inductance is rising. That is high speed. So high speed also you require time for building up the current, and that the torque is typical negative and flux, and then how the portion of psi characteristic you get the work done. Now coming to torque speed with the constant torque region. So the base speed is maximum speed at which the maximum current and the rated torque can be achieved at rated voltage. In this region, the torque is controlled by regulating the current with relative minor adjustment in the firing angles at necessary to elevate the noise or improve the current or torque waveform or to improve efficiency. And in constant power region, at the speed and back EMF increase, the dwell is increased to maintain the peak flux at the highest possible level. And if the dwell is equal to half the rotor pole pitch and the defluxing angle is negligible at the base speed, then in principle the dwell angle can be doubled before the onset of continuous conduction. And this is typically in different zone in motoring and generating: constant torque zone, constant power zone, and falling power zone. So now coming to specific features of high grade control includes high bandwidth torque control, low torque ripple, four-quadrant operation over a wide speed range including zero speed, and your seamless transition from maximum efficiency operation to maximum field weakening with the efficient use of control over voltage. And this control is regarded as the functional equivalent of AC vector control. Now coming to differences between reluctance motor and the classical machines. The classical machine theory of torque control in electric drive is based on the DC machine, in which the torque is proportional to flux into current. The flux and current are controlled independently, and the orientation of flux and the ampere conductors distribution both in space and in time is fixed by the commutator. And in AC field oriented machine control, the mathematical transformations are used in which no effect to achieve the independent control of flux and current, and the commutator is replaced by the soft position sensor. In classical DC and AC machines, the flux is maintained constant, which current is varied in response to the torque demand. In SRM, unfortunately, there is no equivalent of field-oriented control. The torque is produced in pulses, and the fluxes in each phase must usually build from the 0 to and return to 0 in each stroke. The orthogonality of the flux and current is very difficult to contemplate, but because the machine is singly excited and therefore the armature current and field current are indistinguishable from the actual phase current, and the SRM does not have a sign distributed winding to a smooth air gap, therefore there is virtually no hope of field-oriented control. So to achieve continuous control of the instantaneous torque, the current waveform must be modulated according to a complex mathematical model of the machine. And this is typically like an induction motor, then PLDC motor and switch reluctance motor. The torque speed characteristic of SRM are the same in ideal torque speed characteristic of the motor required for electric propulsion. Thus, the SRM is the best candidate for high-speed motoring in comparison to your other motor. And this is typically, you can call it like how your operation with the motor torque density, power density, and maximum density. So you will find the SRM have a good torque density higher than almost equivalent to induction motor, but it has a high power density 1.5 kilowatt per kg, and maximum speed is also 20,000 rpm compared to the even induction motor 15,000. For example, capacity of 20 kilowatt motor. Now comparison of switch reluctance motor versus variable reluctance stepper motor. So normally operated with soft position feedback, this reluctance motor to synchronize the commutation of the phase current with the precise rotor position, and normally designed for efficient conversion of power up to level of 300 kilowatt. And your stepper motor normally run open loop, that is without soft position feedback, and normally designed to maintain step integrity rather than achieve efficient power conversion. Now comparison of reluctance motor with synchronous reluctance motor. This reluctance motor, both stator and rotor poles have cell and pole. The stator winding comprises a set of coils, each of which is wound on one pole. Excitation in sequence for current pulses are applied to each phase in turn, and the phase flux linkage should have triangular or sawtooth waveform but should not vary with the current. And in case of synchronous linkage, stator has a smooth bore except the pole slotting, and stator has a polyphase winding with approximately sine wave distributed coil, and excitation is a set of polyphase balanced sine wave current, and the phase inductance should vary sinusoidally with the rotor position but should not vary with the current. Now coming to direct torque control of switch reluctance motor. So you can have here the reference torque, and you have a speed feedback. From position you estimate the speed, and then with this position you go to control value turn on turn off angle and reference angle, with goes reference current theta on theta off, and then you have a current controller with the current feedback, and it goes switching signal to the converter. So direct torque control techniques have been employed and designed to minimize the torque ripple of for SRM, and the current reference is calculated from current profile stored in the lookup table, including the current torque position characteristic. And switching signals are obtained from the current controller by comparing the sample current and reference current. Now coming to direct instance torque control of SRM. So in case of this, we have a reference torque, we have estimated torque, and we have a stage torque controller to which we give theta on, and then we have a switching signal. But of course, for torque estimator, we have a current as well as position feedback. Now coming to for this direct instance torque control, in instance torque control, the current reference is computed at each sample time according to the torque reference and the rotor position, and the direct instance torque DITC is derived from the DTC. It has a rapid response to the torque error, thus the torque ripple can be reduced more effectively, and the torque reference is directly used for control without transforming into current reference. The instance torque is estimated online, which is directly employed as the torque at the control variable without any current loop, and switching signal are generated by a torque hysteresis controller. Now coming to torque sharing function based control. So the problem of choosing the appropriate current waveform to ensure the low torque ripple becomes the key issue. The production of the torque by individual phases must be coordinated. So unfortunately, there is no inherent inherent unique distribution of torque between phases, so the torque sharing function and the associated current or flux must be designed. And this is typically torque sharing function. So we have a position feedback, and with that and speed, so we go reference torque, we get the 3-phase torque for 3-phase motor, and then we have I theta T table, we get a 3-phase reference current I star I B star I star. Then we have a sense current and give to hysteresis current controller, which give the switching port signal for your converter drive feeding the switch Laplace motor. And this is typically how the linear your torque sharing function, I mean typically for A and B phase and C phase with different color, and how sinusoidal torque sharing function, I mean with the different angles here. In the 2-phase commutation region, the torque references of next phase and previous phase rise to total torque reference and decrease to 0. Respectively, the total torque reference is constant, which is sum of the phase torque references. So therefore, by using the TSF, the output torque can be controlled with a low torque ripple. To reduce the torque ripple of SRM, the torque sharing function with current hysteresis control is usually employed, and torque reference of each phase can be defined by a torque sharing function where the sum of the phase torque reference is equal to the output torque reference, and the phase torque can be obtained from the predefined torque profile in a lookup table, including the Li, I, T theta characteristic. And this is typically how the typical torque sharing function phase torque control is there in the typically in the 2 cases at low speed and high speed, the current different kind of waveform torque. And using flux control, torque control by flux control, we have a position, we have a difference torque, we have voltage feedback from which we get a flux, we have a estimated flux from position and torque, and we have a flux controller which gives the generate the switching signal for your converter feeding the motor. And this is for using current control. So we have a typically torque and feedback with the position and voltage, we get the reference current, and with the current feedback we have a current control and give to converter switching signal which feeds the switch. And this is typically current control using current control. We have a torque reference with the position, we have a switching estimation theta 0, and with this torque we get the current reference, and then we have a P value of current amplitude, and then we have 3-phase reference current with the feedback current. We put a hysteresis current controller for controlling the current in the by the inverter. And this is the flux linkage and actual static characteristic. I mean for the your 7.5 kilowatt your 12/8 motor, the aligned position and the torque versus your typically theta at different currents. Like now coming to position sensorless reluctance motor drive. So why position sensorless? All the position sensor require mechanical mounting arrangement on the rotor shaft, and this requires additional space and increases the total volume. And these sensors may be temperature sensitive and have revolution constraint also. So the cost of these sensors is also high and require a special care during installation and operation. Therefore, position sensorless methods of control are required for the SRM drive. And this is the typically glossy of rotor position measurement, continuous excitation or discrete excitation. Then with the sensor based sensorless, we talk about, of course, for sensor based, we have absolute and incremental radiative sensor, absolute encoder, then resolver with the R2T converter. Then it's expensive, but incremental or magnetic flux is also expensive. For sensorless, we have a modern control theory with the observer, heavy state observer, sliding mode observer, then converter filter, neural network and fuzzy control, and of course with the inductance measurement based method with external signal injection with the demodulation technique, most robust over all vacuum and inexpensive with the current and voltage are sensitive way. Then another is the your constant current or flux engage method is special technique required to overcome magnetic interference. Now coming to your discrete equation with sensor with absolute magnetic thing with the Hall sensor disc with the slots or optical light interrupted and LED and inexpensive, require mechanical sensorless inductance measurement based on the current rise or fall measurement and simulate problem of EMF, mutual coupling, noise in measurement. Now coming to like a position sensorless methods can be classified as open loop methods, energized phase methods and unenergized phase method. So coming to open loop method, it is also known as the stability torque control method. It does not provide the direct position indication and the motor works in open loop as a stepper motor from the variable frequency oscillator in a traditional synchronous manner. An adjustment is made to dwell angle or commutation angle by observing the variation in the DC link current in order to improve the stability in pull-out torque with the maximum efficiency. And coming to energized phase method, it uses the excitation current voltage waveform or derivative that is variable from the phase that is generating torque or to direct the rotor position directly. And one of these methods sends Ti upon dt, which is a function of the rotor position, and the motor is in hysteresis current regulation. Other methods that belongs to this group make use of the regenerative phase current when the rotor crosses the aligned position. And now coming to this energized phase method, these methods mainly are for low speed where the current can be regulated below the motor base speed. These methods, there are methods in this group involving the direction of flux linkage or phase inductance when the rotor passes through a particular threshold value which represents a specific rotor position, and these groups also include state observer method which are based on the mathematical motor model that is run in real time. Now other methods include the irregularity in the stator poles, rotor poles, or both, and in such method the inductance profile is modified so that when the phase is excited it is easy to detect the irregularity in the phase current which indicate the specific rotor position. And the last method uses the shape of current waveform to estimate the position, and a method has been proposed that identify if the commutation angle is leading or lagging based on the shape of the current waveform. And coming to energized phase methods, in this method different kinds of test signals are introduced or measured during the time when the phase is normally energized, that is the phases that are not generating torque, usually during the negative slope of the phase inductance when the machine is motoring. So when the machine is generating, the positive slope of the inductance is used instead of, because there is a region where the phase is not conducting. So now coming classification of loop method, dual angle compensation and commutation angle compensation. Energized phase methods are chopping waveform, regenerative current, flux linkage, state observer, irregularity in stator current waveform. Energized phase methods, active probing, modulated signal injection, regenerative current, and mutually induced system. And coming to dual angle compensation, here we have a typically function goes to oscillator, and then we have a dual angle, and typically from the current sensor, get the dual function stage. Of course, frequency stage there for delta F, and then theta d goes to dual generator, which of course goes to the switch electrons motor drive and converter. This is ANN based position estimation. So we are sensing current and voltage and estimating flux linkage calculator. Then we have a ANN estimator from which we get speed and position, and we have a reference speed. So go to reference of go to speed controller that goes to output as a system control with the position. We get the signal for the converter driving feeding the switch electrons motor. In the flux linkage method, we have a sense voltage, then we have a sense current with subtract Ri from the voltage and integrate, and we get the flux linkage, all fluxes, and from fluxes and multidirectional table of magnetization curve, we get the theta position. And the flux linkage characteristic, here we have lambda versus I, typical I for different theta characteristic with align to align, and these are the typical flux linkage rotor position with the at constant current, and this is flux linkage with rotor position at constant flux linkage. Now coming flux linkage control SRM, so we have a reference speed, we have a sense voltage, sense current. So from this we get the typically the flux by integration, then we get the from sample typically lambda and sample load, we get the lambda given a current, and then we get a memory with the theta lambda theta, we get the position, and then with the reference speed, then estimate position and speed, we go to the control block with the for estimating torque reference, current control, and the gate signal generation, giving a signal to the getting signal to power converter feeding the switch electronic motor. This state observer, we have a reference speed, we have a typically estimated speed which go to controller and converter, and that is typically goes input for the switch electronic motor. Then the from switch motor we have a typically the feedback which go to get the Y, and from the observer also we get the YS, and from which we get the error, and then we get certainly the position and speed from this observer. So coming to state observer method, the linear SRM system equation d lambda upon dt equal to minus RS L inverse theta lambda n plus Vn for n equal to 1 to m, and d omega m upon dt equal to minus b upon j omega m plus 1 upon j summation of n to 1 half lambda n square dl upon d theta minus t upon dl upon j, where d theta upon dt is 1, in is L inverse function of theta with lambda n, and the observer then given d lambda sn upon dt equal to minus rs L inverse theta lambda sn plus Vn plus k1 in bracket in minus isn for n equal to 1 to m, and d omega sum upon dt equal to minus b upon j omega sum plus 1 upon j, and half lambda sn square d lambda s of theta upon d theta minus tsl upon j plus k2 in minus isn, and d theta s upon dt equal to omega sn plus k3 in bracket in minus isn, where isn is L inverse theta is L inverse function of theta and then lambda sn. So errors between the actual and observed variable are in equal to in minus is lambda, in equal to lambda and minus lambda sn, and omega equal to omega minus omega sm, and theta equal to theta minus theta. Using the error variables, we find the error dynamics of the system by substituting from the observed equation. So d lambda en upon dt equal to minus rs L inverse theta lambda en plus Pn plus k1 e1 for n equal to 1 to m, and d omega e upon dt equal to 1 upon j summation of half bracket lambda n square dl upon dls theta upon dt minus lambda square dl upon dt minus b upon j omega e minus tl upon j plus k2 e and theta e upon dt equal to omega e plus k3 ie. Now coming to simple result of Sri Lakshnath motor drive for 3-phase 5-4 pole motor drive. So this is, you can see how the torque developed with the time and how the typically your speed for normal inertia and with the double inertia how it get delayed, and how the current typically the magnitude is added when current waveform during starting. And this is the typically case when load application removal is there. This is the typically the same the net torque and per phase torque, and this is the, again the during starting the your per phase torque and net torque, different phase torque, all 4 phase torque in different room. So coming to now the result for 4-phase 8x6 pole SRM. So this is speed and torque profile, and this is how we can reduce the typically the torque ripple. In first case we have a normal case, and second case we have a commutation angle control, constant torque profile, and same value control angle for minimum torque profile, and see the minimum torque for current by current shaping like. And this is typically the, you can call it the maximum torque versus armature for constant current profile, same value with the minimum. This is flux linkage versus current characteristic, we call it stock. And these are the typically the torque for all 4 phases. These are typically the reversal. During reversal, how the typically the torque, how the current waveforms is there, and typically the starting, how the low speed starting take place, starting that the torque, then the current and the net torque, and then with the comparison of controller with fuzzy logic during starting PID and sliding mode. Now coming to acoustic noise and its control in Sri Lakshnath motor. We have a sources of noise: magnetic, mechanical, aerodynamic, and electronics. So electronics is switching harmonic, and the aerodynamic air, liquid or water cooling, and then your magnetic of course is come from mechanical is the main self load, induced or auxiliary, and for self with the stator and rotor or modes of vibration, bearing, balancing. In balancing dynamically, eccentricity, unbalanced rotor, elliptical rotor, frequency, elliptical rotor both, and load induced coupling or foundation. Coming to noise in SRM, the dominant source of vibration and the acoustic noise in Sri Lakshnath drive is really vibration of the stator, and the arises because of the torque production mechanism in which the force between the excited stator teeth and rotor contains a significant radial component in addition to the required tangential component, and these tangential forces is converted into rotational torque, and the radial force contribute to vibration acoustic noise, as you can see how the force, radial force and caution. So the abrupt change of MMF is caused by the excitation mechanism of the SRM. So to develop the reluctance torque of SRM, the phases are excited one after another, and this means the full magnetization and demagnetization are needed to develop torque for each phase, which introduces attraction and rewounding of the magnetic circuit. This mode of operation also needs high voltage, ampere and reactive power to drive a motor and increase the torque ripple. The two-phase excitation of a step motor could be one of the possible considerations to reduce the noise of full excitation. So SRM with two-phase simultaneous excitation mode can obviously increase the average torque and reduce the torque ripple. Even more electromagnetic coupling characteristics have to be considered. So now noise mitigation, that is magnetic noise mitigation. The radial force in a machine are directly proportional to the square of the flux density in the air gap. One of the obvious ways to reduce the noise would be to reduce the flux density by enlarging the air gap, and skewing is not relevant in the reluctance motor for reason that it will remove the advantage of manufacturing simplicity and will lower the ratio between the aligned and unaligned inductance, thus reducing the power output and power density of the machine. So following standard rules to select the slot number reduces or eliminates the unbalanced magnetic field, blocking and crawling in AC machines, and vastly help to reduce the noise and vibration in machine. So magnetic noise is due to rotor eccentricity will accelerate the radial force unevenly, resulting in additional noise generation, and manufacturing the rotor with tight tolerances will mitigate the problem. So now coming to noise with the active noise cancellation scheme, the two-stage commutation method and voltage smoothing method, and three-stage commutation and extended filtering method. And these two-stage commutation, how we really do that, typically the voltage and zero voltage and the negative voltage. So here two-stage commutation needs for single voltage pulse generation, and voltage smoothing, typically the voltage for single voltage pulse operation, and the three-stage commutation. Then you can see the waveform in three-stage commutation. Then the extended filtering method, typically for current pattern. And disadvantage of noise cancellation technique is even the best method, two-stage commutation, requires at least half the resonant cycle. This is why the considerable and will adversely affect the torque generation and power output along with the dynamic control of the drive system. Therefore, these techniques may be more suitable at low speeds than at high speeds. And this is typically hardware setup for SRM drive, with the different component. And this is typically the hardware setup for different parts of the total circuit of motor, brake and entire assembly. Now coming to the case study, typically power quality improvement in SRM drive. So if we take a simple diode rectifier and then multi-phase reluctance motor, so we find the current in supply, the peak current, the voltage. So the conventional scheme of SRM drive fed by diode rectifier draws a non-cyclical current from the AC mains, which results in a high current TAD of order of 70 to 80% AC machine, and where the displacement factor is cos alpha nearly equal to unity, and distortion factor 1 upon 1 plus TAD square, low at TAD 60 to 80%. So power factor is DF distortion factor into displacement factor value of order of 0.6 to 0.7 due to distortion factor, and this experimental result power quality is for conversion with the diode rectifier. So you can say here power factor is 0.64 and TAD is 74.9 of supply current in single phase diode rectifier feeding the SRM converter. And now of course for power factor correction converter we can have buck converter, boost converter or buck boost converter. So power quality converter are highly recommended to reduce the TAD and to obtain high power factor. So this is a classification of AC/DC buck boost, PFC based buck boost converter in SRM drive. So we have a non-isolated single output buck converter, CSC converter, cuck converter, Leo converter, capacitor converter, CP converter, zeta converter. And then we have non-isolated dual converter, buck boost converter, cuck converter, cuck 1 converter, Leo and CP converter, and typically zeta CP converter, cuck 2 converter, and cuck CP converter. And then isolated single output, Piper red, cuck converter, CP converter, or CSC converter, Leo converter, zeta converter, and isolated dual output integrated CP flyback cuck converter by CP converter, then integrated zeta converter, Leo converter, zeta converter, and then bridgeless single output, the bridge buck boost converter, say cuck converter, CP converter, and CSC converter, and dual converter and zeta converter, and bridgeless dual out buck boost, cuck, switch capacitor, and CP converter, and then the half bridge buck boost, Leo converter, and zeta converter. And this is different modes of operation. You can operate power factor correction converter in continuous conduction mode, how the current looks like supply current, then discontinuous conduction mode, the current, and then critical conduction mode with the power called boundary condition current mode. Now PFC mode with the continuous conduction mode, a smaller inductor current triple, low EMI, low root mean square currents on the throw inductor and switch, operate at hard switching and out suffers from reverse pickup. And discontinuous conductor mode features zero current turning on for the switch, operate in the constant switching frequency, which beneficial for designing the inductor and EMI field. An inductor size is reduced, thus reducing the board space and constant of magnetic material required, and high EMI. And critical conduction mode, zero current turning on of the switch, soft switching, no reverse recovery of diode, customized design, thus saving the magnetic material variable switching frequency operation, resulting in a different difficulty in the design of the inductor and EMI filter. And this PFC converter for midpoint converter, especially 4-phase, non-isolated with single-phase unidirectional bidirectional, 3-phase unidirectional bidirectional, and isolated single-phase unidirectional bidirectional, and 3-phase unidirectional bidirectional. So coming to some simple topology for midpoint converter for SRM type. So this is typically a boost converter, single-phase 3-level PFC converter, which gives the midpoint. Stabilization also. So after diode rectifier with a small LFCF filter, we have a inductor. Then we have a 2-switch boost converter so that we can charge the both capacitor equally. Then midpoint converter. Then another single phase neutral point rectifier for midpoint converter. So here, of course, this is for bidirectional. So we have this diode clamp where we connect single phase, and then it gives the midpoint equal voltage for your 4-phase motor with the midpoint converter. Then you have a single double boost midpoint converter. So after diode rectifier, you have 2-switch with the inductor and midpoint converter fitting this. Then you have a Minnesota rectifier which give equal voltage in the output with a 3-phase supply, of course unidirectional converter. Then you have a typically a 2 edge bridge converter with a transformer isolation and fundamental frequency transformer isolation with 2 edge converter giving equal voltage for these capacitors. Then you have a Vienna rectifier which gives the equal voltage on midpoint output midpoint capacitor. Then you have a 3-phase 3-level neutral point capacitor midpoint converter for bidirectional 3-phase converter for 4-phase. Then you have a 12-pulse AC/DC converter with your high pass filter which give a 2 equal voltage from 2 6-pulse converter with the phase shift. And the 4-phase, this is your 3-phase is got connected to boost converter giving equal voltage across the capacitor. Then 4-phase. Then typically again is got connected with 2 voltage source converter, single phase voltage source converter, HB converter giving equal voltage to midpoint converter. Now coming to analysis of SRM type, is single phase 3-level power factor correction converter rectifier. So this is typically first topology single phase 3-level PFC rectifier. So after diode rectifier, we have a LC filter, then inductor, and then 2 switches with the typically to give a midpoint with the 2 diodes and the 4-phase SRM. So coming to inductor current controller, the sense voltage of DC link is compared with the reference DC link voltage, and the resulting error voltage at the nth instant given as VDC E equal to VDC star minus VDC. This error given to PI controller to get the magnitude of the reference inductor current ILM, and is given to at sampling instant. So ILM n star equal to ILM n minus 1 plus KP1 in bracket VDC E n minus VDC n minus 1 plus KI VDC n. This magnitude multiply the absolute value of the unit template of AC supply voltage 10 from single phase PLL to get the reference inductor current IL star, and is given as so IL star equal to UT into ILM star. So this reference inductor current is compared with the sense inductor current and is given to carrier based pulse width modulation to get the PWM signal A1. So the capacitor voltage controller, the 2 capacitor voltage VC1 and VC2 are compared, and resulting capacitors and voltage error at the nth sampling instant are given as VCN equal to VC1 minus VC2, and the PWM output of the capacitor voltage controller is A2 equal to 1, V3 1 is greater than VC2 and 0 if VC1 is less than. So region selector, so signal as A3 generated by comparing VS with VDC by 2 and is given as A3 in by 1 or 0 if Vs absolute is greater than Vd by 2 or Vc absolute is less than Vd by 2. And they typically control is same for single phase 3-phase. So we have a DC link voltage reference VDC star and VDC. goes to PI controller, which give one signal, and then we get that gives the amplitude, and we have a pump sense voltage, the template, and we get a reference current. We take a feedback current and give to the current controller for distribution. We have, of course, the two capacitor voltage equalizing also. Then we have a supply voltage with band pass filter and DC-link voltage for A3, and with the 3 signal A2, A3, we get the switching signal for SA, SP. And these are the experimental results. You can see supply voltage, supply current, and then the DC-link voltage and the motor winding current typically. And then we have your inductor current, on which typically have a in phase with, and these are typically the DC-link voltage and capacitor voltage, VC1, DC-link and VC2, and VC1, VC2, which are equal. And then the typically the 4-phase winding current of the motor and supply voltage, supply current. And then the typically for the case of dynamic performance 3-phase, with this set is starting, and then with the step change in the load pump, and the typically for the dynamics corresponding to step change in the load 50 to 1 full load and pump 50 load to 1, and the typically your dynamic performance for the again with the your load change and the change in the load pump, and this is typically your dynamic performance single phase with the speed change from 1200 for them, and then the from 1200 for, and the performance 3-phase some drive at step change in the speed from 1200 to 1400 RPM. These are power quality performance that typically you can call it at full load. We get the 3.7% TAD with the unity power factor, as well as for half the load also we get 4.6% TAD with the unity power factor. Now coming to input current versus load torque. Input current TAD with the load torque with 3-phase plumb rectifier. So you can see how the TAD remain less than 5% for different kind of converters. Now coming to analysis of SRM drive with buck boost and derived buck boost converters. So this is typically a buck boost converter, which with the you can call it designing per inductor in DCM. It gives inherent power factor correction with the for the output. So these are the different mode: device conducting, output conducting, none of the conducting, and the waveform. And these are the experimental waveform that how the your let's say supply voltage, supply current, and winding current, and 4 winding currents, and the DC-link voltage. And this is typically the inductor current, how it is designed DCM, and the power quality performance. So we get a typically at very low power we get TAD power factor 0.987 per flow, and typically at full load we get the 4 at 170 volt we get the 4% TAD power factor unity, and 270 also we get the power factor unity with 2% TAD. The dual switch, dual buck boost converter, as you can see, 2 converters are used for getting equal voltage, and design at these inductor LO1, L2 as in DCM, so that you get inherent power factor correction. So we control the only DC-link voltage for controlling the speed. And then this is the mode when device conducting, diode conducting, and none of the 2 conducting and waveform. And the design value for the inductors, DC-link capacitor, filter inductor, and capacitor to capacitor, and the starting performance typically for reduced phase current. And then the performance under steady, you can see supply voltage, supply current remain in phase. So you get both the inductor current discontinuous, then the DC-link voltage, both the capacitor voltage, then 4 winding currents, torque and speed and torque. Then during the typically your drive and DC-link voltage change 160 to 320. Supply current remain in phase with the supply voltage, and harmonics are also less. This is for dynamics of the drive for typically during supply voltage variation. Then the switching stress on the devices, and this is the typically you can see at the varying DC-link voltage at different speed. We get the power factor 0.99 in most of the cases, as well as TAD quite low, less than 5-6%. So harmonic full load is 2.8% of supply current. There another converter, modified bridgeless buck boost converter for SRM drive, and different modes of this positive converter, negative converter, and then the design value of component, and the typically your motor starting with reduced phase current, and the steady state waveform you can see of supply voltage, supply current, and inductor current are discontinuous, and the DC-link voltage, both capacitor voltage for winding current, torque and speed. And this is for the case of dynamic pump and DC-link voltage change from 160 to 300. Then the supply voltage variation, and the typically the your switch voltage, switch current waveform, and switching stress, and TAD of supply current typically at 3.68 at full load. And this is another SAPI converter for SRM drive. So different modes, device conducting, switch conducting, and none of the two are conducting. They are the design values and the waveform for steady state at full load. So you see supply voltage, supply current in phase with the supply voltage, then the inductor current continuous, and then the output inductor is designed in DCM, and your DC link voltage and both capacitor voltage and 4 winding current and torque and speed. This is for the case when you change the speed from 320 volt DC link to 120 DC volt and change from to supply voltage variation about 220, but supply current remains sinusoidal in phase with the voltage. Then this is starting performance. Then the stresses and TAD 1.84% at ready condition. This is a modified SAPI converter with the midpoint and the different modes of it. Then the current typically waveform of the different signals, the design parameters, and the starting performance like of this motor with the converter, and then the steady state result you can see supply current in phase with the voltage and DC link voltage, then both capacitor voltage, 4 winding current, the developed torque with the motor and speed. And this is for the case of when DC link voltage change from 160 rpm 320 rpm for control of the speed. This is for the case of supply voltage variation from 220 to 170. Then the dynamic performance at your typically steady state performance, the supply voltage, you can say supply current is in phase with the supply voltage and almost sinusoidal. The stresses of converter, then the Coulombic distortion of supply current 3.8%. The Cuck converter, which is used for again for output inductor GCM to get power factor correction with the only voltage control for speed control. 3 modes: device conducting, diode conducting, and none of the two conducting. And the modes of operation of Cuck converter. This modified Cuck converter, and the 3 modes of device conducting, diode conducting, none of the two. And the another mode, the typically the waveform for different modes. This is your dual output Cuck converter. Then how the different modes and waveform and design value. These are starting performance. And then the steady state performance, you can say supply voltage, supply current, okay, and the inductor current, then output inductor current is discontinuous for both the inductor, and then DC link voltage, both the capacitor voltage for winding current, then the torque and speed of the motor. This case for when DC link voltage control for speed control 160 volt to 320 volt, then the supply voltage variation 220 to 170, all the parameters, and the supply current TAD around 3.03%. Is another dual output bridgeless Cuck converter SRM drive with equal voltage and different modes of operation, ideal perform, the design parameters and experimental result. You can see here typically supply current in phase with the supply voltage, 4 winding currents, and the both capacitor voltage and different voltage. Then the typically the output inductor current is continuous, input inductor continuous, and capacitor voltage continuous. For just demonstrating the switch the parameter, the power quality performance. So you can see TAD remains less than mostly in except a very light load, which is 8.7 otherwise, but power factor remains almost close to unity in most of the case. And then of course you can see how new bridgeless, without bridge, how the TAD power factor improved and TAD also reduced, and then the duty cycle varies. This is the case of Zeta converter typically for the control, and the different mode device conducting, diode conducting, none of the two conducting, and waveform design parameters, and the simulated waveform. That your supply current is continuous and for winding currents and torqueable. Then supply voltage variation per month. Then your DC link voltage control for speed control, and the supply current TAD of order of 40% to light load and full load 2.3%. And your all other performance parameter. Then bridgeless Zeta converter fed SRM drive and different mode device conducting, diode conducting, now two conducting, and waveform and design parameter. And the comparison, where power factor remains almost 199 and TAD remains less than 10%. Another switch capacitor converter, then different modes of switch converter and the parameters, then starting performance, then your steady state performance, and you can see the supply current in phase with the supply voltage and sinusoidal, and then the typically speed control from 320 to 20 rpm, then the typically the load variation and supply voltage variation, and TAD remains 1.43%. Then the canonical switching converter feeding SRM drive, different mode device conducting, diode conducting, none of the two conducting, and waveform. Then the parameters of converter and supply. So you can say here the inductor current is discontinuous, and you get supply voltage in phase with supply current. Supply current get in phase with supply voltage and almost sinusoidal. Then the variation of DC link voltage for speed control. Then the supply voltage variation 220 to 270, performance at during starting. Then you demonstrating switch voltage, switch current. Then the TAT of supply current of 2.61%. Then the dual output LEO converter. The switch conduction device conducts none of the two different modes and waveform, and your data of design data. Then starting performance. Then steady supply current you can see in phase with, but you can see the typical inductors, output currents are designed in DCM, and the motor performance. For then total DC link voltage variation for speed control, and supply voltage variation, and stresses, and TAD of supply current 3.83%. Then the experimental performance supply current you can see in phase with the supply voltage almost 5% DC link voltage, and winding current at low speed and high speed. Then the supply voltage, supply current at typically when all by 4 winding current. And the inductor current is typically the parameter capacitor voltage, inductor current discontinuous, capacitor voltage continuous. Parameters experimentally for all modes, and you can see discontinuous current mode. The stresses, starting performance, then the steady state, the DC link voltage control, and typically supply voltage change, and the power quality performance. TAD remain always less than 3.8%, and power factor almost close to unity at different voltage, 90 volt to 70 volt, as well as and light load and full load. Another converter, dual output converter, power factor pad. Then the different modes, waveform, typically an experimental result. So you can say supply voltage, supply current is in phase with the supply voltage and DC link voltage. 4 winding currents at low speed and high speed. Then typically performance and speed control, 2 different speed, 300 volt DC link and 100 volt DC link, and typically the your waveform during different mode of operation, starting performance, and then the power quality performance. So TAD remains less than 5.2%, light load is 9.8%, but power factor is close to 0.98 or 9. So half bridge dual output converter with bridgeless in different modes of operation, waveform, and the experimental result you can see typically the supply 4 winding currents, and typically the DC link voltage. Then supply voltage, supply current you can see in phase with the supply voltage for both the speed at 300 DC link and 100 DC link voltage. Then the typically supply current and the inductor, typically the switch voltage stress, the enlarged view of that, and supply voltage variation 150 to 7 is speed control, and DC link supply voltage variation and starting, and the switch stresses, and TGD of supply at full load 1.7%, power factor is unity, and here under light load also perfect unity with 2.1% TAD, and the 170 volt also TAD is 1.6% with the unity power factor. Then typically at low power also TAD is 3.5% unity power factor. Now coming to another case study, SRM drive for solid water pumping. So here in case of solid water pumping, we have a PV array, we have a boost DC converter, then SRM, and we have of course battery bank required, and then the position and speed sensing for converter control and DC link voltage. So this is typically the converter topology 2 for single stage directly is feeding converter, and with the MPPT we obtain from the PWM control, and this is with the battery connected typically. Now so here it is a typically PV array drive with the water pumping with utilizing a CUC converter. So CUC converter is responsible for MPPT, and then DC link voltage is controlled inherently, whatever energy is fed, and decide the speed of the motor. Segmental setup, and these are the typical waveform of the phase current of SRM, then neutral current typically, and you can call it the capacitor voltage, inductor current, and then the starting typically performs speed control change, then the canonical switch converter for MPPT and driving the motor, and the different waveform PV voltage, PV current, PV voltage, power, and DC link voltage, and the 4 winding current for 2 different insulation solar 600 watt per meter and 1000 watt per meter square, and then the winding current at 1000 watt per meter square, the soft starting, then your MPPT performance at 600 volt watt per meter and 1000 watt per meter square, and the control of with the Leo converter and the experimental waveform with the Leo converter for starting, and MPPT performance for 600 watt and 1000 watt. Then your typically performance of this with the dual output converter and the experimental waveform, typical steady factory operation and starting performance. Then the MPPT performance over 600 watt, 1000 watt. Then your single stage directly SRM die with film control is responsible for MPPT and the experimental performance for demonstrating your different encoder signal, then starting and insulation change. Then MPPT performance 600 watt and 1000 watt per square. Then we have integration of the battery along with, of course, boost converter feeding through, and the battery integration with buck boost converter. And then, of course, these are the different modes without battery, with battery, and all the modes. And then this is starting performance of the motor. Then the insulation change of the solar. Then again the starting performance and the soft starting of the motor. Then the insulation change and MPPT performance. Now coming to typically solved numerical problem. So coming to example 1, in the 3-phase reluctance motor with the 6 stator and 4 rotor poles, width of stator and rotor is same as 40 degree, the line inductance 12.7 millihenry and the line inductance 1.5 millihenry. The peak current of 16 ampere in phase winding is fed when the inductances are increasing. So calculate the torque developed by the motor. If the developed torque is required double of this value, calculate the required peak and RMS current in the winding, and saturation is neglected. So solution is theta 1 equal to half in bracket 2 pi upon PR minus beta s plus beta r. So that theta 1 comes 0.73 radian and maximum inductance occurs at theta 2 equal to 0.7854. Having no saturation opening, so slope is LA minus LA to theta 2 minus theta 1. So it comes 0.01604. So torque is half pi square dl upon theta, putting value it comes 2.0538 Newton meter. Since the required torque is double the rated, so therefore the peak current of the motor winding IP equal to under root 2T upon dl upon theta is come 22.631 ampere, and RMS winding current is your under root PR upon 2 pi theta 1 theta 2 IP square d theta. So putting value it comes 15.08 ampere. Now coming to example 2, what is the step angle of 3-phase reluctance motor having a 12 stator pole and rotor pole, and what is the commutation frequency in each phase at a speed of 6000 rpm. So solution is step angle theta equal to 2 pi upon q PR, where q is the number of phase, PR is the number of rotor pole. So theta is 2 into pi upon q PR, that is 15 degree, and commutation frequency is f1 and PR, and that comes 800 hertz. Now coming to example 3, what is the step angle of 5-phase reluctance motor having a 10 stator pole, 4 rotor pole? What is the commutation frequency in each phase at a speed of 6000 rpm? So theta equal to pi upon PR. So putting a value, it comes 18 degree. Commutation frequency is f1 and PR, that comes for 100 hertz. Example 4 is reluctance motor with 6 stator poles and 4 rotor poles, has a stator pole arc of 30 degree and rotor pole arc of 32 degree. Aligning reluctance is 10.7 millihenry and the unaligned inductance 1.5 millihenry. The saturation can be neglected. Calculate the instantaneous torque when the rotor is 30 degree before the aligned position and the phase current is 7 ampere. Neglect the pin. So solution is torque equal half Li square d upon d theta. Theta 1 is half 2 pi upon PR minus beta s upon beta. So from minimum inductance occurs at unaligned point theta 1 equal to 0.24 radian and maximum inductance aligned position, that is theta 2 equal to 0.76. Having no saturation, slope is LA minus LU upon theta 2 1, and it comes 0.175. T rated is half pi square d upon d theta, putting value 0.43 Newton meter. Now coming to example 5, 4-phase 4 kilowatt 1500 RPM reluctance motor with 8 stator pole, 6 rotor pole, has a stator pole arc of 30 degree and rotor pole arc of 22.5 degree. The unaligned inductance is 110 millihenry and the unaligned inductance 11 millihenry. Resistance per phase is 1 ohm. SRM is fed from a battery of 280 volt used to supply 4-phase stator winding of the motor. The motor is used to as an industry as a pallet truck. तो calculate the average battery current, peak winding current and the RMS winding current to obtain the instantaneous torque 8 times the rated torque at starting when the two phases are excited simultaneously, neglecting the saturation. So now solution is rated torque equal to P upon omega. It comes to 25.46 Newton meter when two phases are conducting. So torque by each phase 8 into rated torque by 2, that's 101.86, and d theta is beta r, that is 22.5 degree equal to 0.396 radian, and from torque equation T equal to half square del upon d theta. I current comes under root 2 into T d theta upon d L. It comes 28.42, and RMS current is P upon 2 pi 0 to VR I theta square. So putting value it comes 17.4 ampere when two phases are excited simultaneously. So average battery current IDC 22.5 into 6 upon 362 into IP. So that is 21.31 ampere. Now coming to example 6, a switch reluctance motor with 12 stator and 8 rotor poles has a stator pole arc of 10 degree and rotor pole arc of 16 degree. The underlying inductance is 80.5 millihenry and underlying inductance is 12.5 millihenry. So saturation can be neglected. Calculate the instantaneous torque, and the rotor is 30 degree before the align position and the phase current is 59. Neglect anything. Coming to solution, the rotor pitch is 360 by NR, that is 45 degree. Inductance profile line will be having increasing of 10 degree. So beta is equal to 10 degree and beta r is 116 degree. So before 30 degree of align position, the inductance will have a negative slope. So the torque developed is T equal to half pi square del upon theta, comes minus 43.83 Newton meter, as you can see here in case of diagram. Now coming to example 7, in the 3-phase reluctance motor with 6 stator and 4 rotor poles, poles width of stator is same as 40 degree, aligning inductance 10.7 millihenry and aligning 1.5. The current of 10 ampere is in phase winding applied when inductance is increasing. Calculate the average torque developed by the motor for flat current for width of 20 degree, for 30 degree, 40 degree. So here is the different you can call it waveform, what kind of waveform we have for all the three conditions. And now coming to solution, torque produced by any phase when the inductance are increasing, the constant torque exercise T equal to half I square del upon d theta, it comes 0.6589 Newton meter, and rotor pitch 360 by NR, that comes 90 degree. When conduction is 20 degree, the average torque produced by motor is average torque by the motor during one rotor pole pitch 16 to T upon 90, that comes 0.14926 Newton meter. When conduction is 30 degree, average torque produced by motor, average torque motor in one rotor pole is 90 into T upon 90, that comes 0.6590. When conduction is 60 degree, the average torque produced by motor, that is 30 degree into 2T plus 60 into T by 90, that comes 0.8785 Newton meter. Now coming to example 8, a 4-phase 1.5 kilowatt 500 RPM reluctance motor with 8 stator and 6 rotor poles has the stator pole arc of 30 degree, rotor arc of 22.5 degree. The aligning inductance 25 millihenry and the unaligning inductance 2.5 millihenry. The resistance per phase is 0.25 ohm. Saturation can be neglected, and a device converter platform battery of 48 volt used to supply 4-phase stator winding of the motor. The motor is used in industry as a pallet truck. So calculate the average battery current, peak current, RMS winding current to obtain the instantaneous torque 8 times the rated torque at starting when two phases are excited simultaneously. B, the average battery current, and the peak and RMS winding current are rated of 50% of the rated speed when the only one phase is excited. So coming to solution, A, at 500 RPM, omega R rated is 52.3599 radian per second. So torque is T rated equal to 1500 upon 3%. So it comes 28.6479 Newton meter, and minimum inductance position theta 1. Putting a value, it comes 0.06545, and maximum inductance region theta 2 equal to your theta 1 plus beta x, that comes your 0.5890 radian. As you know, saturation of dl upon dt is LF minus LU from theta 2 minus theta 1. So it comes 0.4298. The peak winding current is IP under root 2T upon dl upon dt. It comes 36.5114 ampere. And RMS winding current is your under root PR upon 2 pi theta 1 to theta pi d theta. So putting a value, it comes 25.82. So motor can have a starting torque 8 times the rated torque if two phases are excited simultaneously. We double the rated current in the winding, provided the rotor must be in the rising inductance zone to produce 4 times the rated torque per phase that is starting. The peak current has to be double. Therefore, the peak winding current is IP equal to 2 IP equal to 73.03, and RMS winding current RMS by into root 2, that is 36.51 ampere. Coming to example 9, a 4-phase reluctance motor with a 8 stator and 6 rotor pole. The pole width of stator and rotor is same at 20 degree is used to in light electric vehicle motor. The line inductance is 110 millihenry and unline is 15 millihenry, and the current of 20 ampere in phase winding are applied when the inductance are increasing. Calculate the average torque developed by the motor in a flat top current with 10 degree, 15 degree, 20 degree. So you can see the waveform how it look like. So torque produced any phase when the inductance are increasing constant current. So half I square dl upon dt, putting a value comes 54.431 Newton meter. And now stator pole pitch is PS equal to 45 degree, rotor field with VR equal to 60 degree, angle between the inductance 60 minus 40 is 15 degree. So when conduction 10 degree, the average torque produced by the motor equal to average torque one pole pitch, that is 40 T upon 60, that comes 36.287. When conduction 15 degree, torque produced by motor is average torque produced by the motor doing 1. So 60 T upon 60, that comes 54.431 Newton meter. And when conduction 20, so overlap angle is beta 0 minus 15 degree, that 5 degree. Average torque produced by the motor is 5 into 4 into plus 60 into T upon 60, that comes 40 upon 60, so 72.5746 Newton meter. Now coming to example 10, in a 3-phase 10 kilowatt 1500 RPM reluctance motor with a 12 stator and 8 rotor poles. Pole width of stator and rotor is same as 20 millihenry. The line inductance is 110 and millihenry, and line 11.5 millihenry. A current pulse of 20 ampere is to be established in the winding current at the position at which the inductance are increasing at 1500 RPM. Calculate the instantaneous torque developed by the motor for a flat torque current in one phase, the advance angle and extension angle, so that it does not develop negative torque. So coming to solution, since theta 1 equal to half pi upon n minus beta plus beta, so beta is equal to beta 20 degree pi in 180 into pi 0.3491. So minimum inductance occur at theta 1, that comes 0.043633 radian, and maximum inductance is your theta 2, 0.392. Assuming that no saturation, so your dl upon theta is your beta is minus mu 0 mu a minus mu l mu upon l a upon d, so it comes 0.2841, and t stands a half I square dl upon theta 56.83. For advance angle calculation, the value of inductance corresponds to the line. So theta advance is equal to your lu I omega upon p upon I phase. So putting value 0.725 for exchange, calculate the value of inductance corresponds to the line. So exchange is I into w upon v phase, that comes 0.6957 radian. And these are the references which are used for developing this lecture. And thank you.